I'm super glad to be here to talk about Nervos and blockchain. So I want to give a little bit of introduction of myself. So I started my research on blockchain since 2011 and did a lot of things since then. I once built an exchange which is open source on GitHub, and I built a Ethereum pool, which is the second largest Ethereum pool in the world right now. And we created Untoken, which you might know is a mobile wallet, which is the most popular mobile wallet in China. And we created permission blockchain, which is called COSIC, and it's being used in banks in China. And now we started a project we call Nervos, which is a permissionless blockchain. I'm going to talk about. I also once worked in Ethereum research team, so on Casper Sharding stuff. Okay. So so today I want to talk about what should the next generation of blockchain should look like. Okay. So because now we have Bitcoin, we have Ethereum, right? What should we do next? So so today I think most of us are pretty clear that what we want is a crypto economy. By crypto economy, I mean things like prediction market and crypto games like CryptoKitty. All those dApps we built upon Ethereum. But the problem with Ethereum is we are facing the trilemma, the scalability trilemma, right? We can't have all those three properties at the same time. We can't have scalability, security, decentralization at the same time. And if we can have all of them, we can build a crypto economy upon Ethereum, because it's just not efficient enough. It can support all those games or dApps running at the same time. So how can we solve this problem? Today, I think most researchers and developers in this space believe that the future is a layered architecture. Okay. We need to solve all those problems by using multiple layers. We can solve the trilemma in a single layer. Like we can make Ethereum to be scalable by itself. But if we create many layers in this network, we have layer 1, layer 2, just like internet, right? We have TCP layer, IP layer, and application layer. We can solve all those problems at different layers, and each layer only need to focus on one problem. Like in layer 1, by layer 1 I mean like Bitcoin, Ethereum. We only need to focus on security. We don't need to worry about performance or scalability. We just make layer 1 as secure as possible. And on top of layer 1, we build layer 2. Okay. And we can solve the scalability problem on layer 2. By layer 2, I mean all those projects, and this is a projects people are exploring right now. So by using these 2 layers, or maybe more layers, layer 0, layer 3, we can solve the trilemma with this layered network. And all those layers combined is still a decentralized network. We don't need to sacrifice decentralization over. Right? So I'll give you some concrete description of layer 2. What is layer 2? Right? I assume most of you are already familiar with Bitcoin. And I'll explain layer 2 and Ethereum a little bit. So Lightning Network, this is the most famous layer 2 project. The basic idea is quite simple, which is I can batching transactions in layer 2 and settle the final result back to layer 1. It's like I want to pay rent, okay, I can continuously pay rent by 1 cent, 1 cent, 1 cent. And rent will accumulate like 100 times 1 cent. And the total is like one euro, right? And all those continuous payment happens on layer 2. And it happens in a P2P manner, which means I have a direct connection with Ren. And I send the transaction directly to Ren, and it's not broadcasted to the whole network. And the transaction doesn't need any global consensus. It only needs to happen between me and Ren. And all those intermediate transactions, they don't need to happen on layer 1. They don't need to be observed by nodes in layer 1 in Bitcoin network. And Ren just need to settle the final transaction down onto Bitcoin, which is just 1 euro, right? So this will scale the capability of layer 1 like infinitely, because we can do all those intermediate transactions without of being aware by layer 1. It's happened in a P2P connection between just me and Ren. It's not even known by the whole underlying layer 1 network. So it's both more efficient and has much better privacy, because it's not known by the global network. That's the basic idea of Lightning Network. Okay. And people are trying to generalize Lightning Network to make it work for smart contracts, because payment, you can think payment as a special case of smart contract. Right? On Ethereum, people can issue tokens as they wish. So like any token is just a special case of smart contract. So people want to generalize this idea and make Lightning Network into state channel. And state channel is what is being actively researched on Ethereum. There are a lot of teams working on this. And there are also Plasma, which is a little bit different than Lightning Network. The basic idea is we still have layer 2, but the layer 2 itself is also a blockchain. So you have layer 1 Ethereum, okay, and you have layer 2, which is also a blockchain, and all those intermediate transactions happens on the layer 2 blockchain. You'll get extra benefit if you use blockchain as a layer 2 instead of a direct, simple connection between people, such as you don't need to always be online, or you don't need to open channel at the beginning, which is a problem of Lightning Network. If you want to use Lightning Network, I have to open a channel before I want to pay rent. I need to create a channel as a first step. But if you are using Plasma, you don't need to do that. You can just send people as they already have an account on layer 2. So that's more convenient. And the idea of Plasma, the interesting part of Plasma is it's in the idea is in an inverse setting compared to Lightning Network. If you want to settle your payment or down to layer 1, it's like you propose a withdrawal transaction on layer 1. Like I have paid rent like 10 euro on Plasma network, and now Ren wants to withdraw this 10 euro from layer 2 to layer 1. He just needs to propose, I want to withdraw 10 euro, and wait someone to challenge. If there's nobody to challenge him, he will withdraw successfully. If there are anyone want to challenge him, anyone sees that you are doing fraud withdrawal. It's not a valid withdrawal. He need to submit some proof, cryptographic proof to layer 1 to claim that Ren is doing some invalid withdrawal, and the layer 1 will going to judge, and if it's really invalid, the layer 1 will punish this withdrawal, will punish Ren. Okay. So in plasmas, the whole plasma idea is using layer 1 as a judge system, as a court, and push all those ordinary events to layer 2 to scale layer 1 in such a way, right? It's just like our human court system. Right? We have Supreme Court, and we have a local court, and we do all our businesses without court, right? We just transaction directly, and if there's something bad happens, we go to court. We go to court and looking for their help, and let the court judge who is right and wrong. So in Plasma, we are using blockchain in this way to scale blockchain, to make blockchain focus on the things that's really important, not ordinary events, but those events with dispute. So there are a lot of ideas happening in this space, ideas floating around in this space. Okay. So in Nervos, we want to build a layered network. The difference between Nervos and Bitcoin or Ethereum is we want to build this from a how do I describe? Because we have recognized that layered architecture is the right solution to the trilemma. Right? We need to think about a layered architecture at the very beginning, instead of, like, if you consider Bitcoin or Ethereum, it's designed for payment or designed for decentralized apps. It's not designed for another layer. Like if you want to design internet, right? You will design all those protocols at the same time. You will design like IP protocol or TCP protocol. You will design them together. You will create them together, instead of someone create IP protocol and someone else creates TCP. Right? You need to consider the whole stack, the whole protocol stack. So in Nervos, we are doing things this way. We want to create a layer 1 that is suitable for all these layer 2 solutions. Okay. And if we think in this way, we need to think about what does such a layer 1 should look like. Okay. So it's easy to see the first requirement, which is it must be powerful enough. It must have the capability to interact with layer 2, which means Bitcoin is not suitable for this purpose, but Ethereum is suitable. That's why the Lightning Network progress so slow on Bitcoin. In my opinion, it's because Bitcoin has a very limited programming model and virtual machine. You can program on Bitcoin, but the virtual machine is quite limited. So you can do a lot of things, and you need to, and it's hard to do anything based on Bitcoin. But it's quite easy to do those things on Ethereum. It's because Ethereum has a built-in virtual machine which is Turing complete. Okay. And so Ethereum has this concept called EVM, which is Ethereum Virtual Machine. It's just a virtual machine like JVM. You can write you can write any code. You can write any kind of program on top of Ethereum and let it be executed by EVM. Like you can, the most popular programming language on EVM right now is Solidity, which is a JavaScript style programming language. So on Ethereum, it's easy to do this programming, and it's much easier to write the protocol implementation to interact with layer 2. That's why most of these layer 2 solutions are happening on Ethereum right now. But there's a second requirement, which is, I call it asset must be the first class citizen. So this is a more complicated concept. So here the first class citizen is like function is first class citizen in functional programming. So you can direct manipulate functions in functional programming. You can pass them as arguments and return functions as return values. Right? So in a blockchain network, we think asset must be the first class citizen, which means you need to be able to pass assets around, pass them between layers, right? We need to exchange assets between layer 1 and layer 2. If you think about blockchain or layers in this way, you will find that Bitcoin fits this requirement, but Ethereum doesn't. Why do I say that? So in Bitcoin, we use a state model named UTXO model, which means we split the state of Bitcoin ledger into this small unit like this. In this, we call this small unit UTXO, which is basically consists of two fields: amount records how many coins is in this unit, and lock is a script, which basically express the owner of this unit. So you can write a code in lock to express that only Jen can unlock this UTXO by signing this UTXO. Okay, so if I provide a signature, I can unlock this UTXO and spend it. This is Bitcoin. This is the data structure for Bitcoin in Bitcoin system. Okay. So, and in comparison, here is the state model of Ethereum. In Ethereum, we have small unit called account. It's like account in bank. Each account has an address, and the address corresponds to your private key. And Ethereum records, Ethereum save your Ether balance in your account. So it has a field of balance. And cold storage, you can just ignore that. That's for smart contracts. So Bitcoin and Ethereum use quite different state model, and they are actually looking at the distributed ledger in different perspective. Because we can consider distributed ledger as a bunch of records, records who owns what is asset, who owns what asset. So you can model the ledger from the assets perspective, because itself, this thing is the coin itself, and it starts from coin and records who owns this coin. But account model, okay, it starts from like who? It starts from people, and the records, these people owns how much coins. It's two different perspectives. The problem with account model is all those assets are aggregated in this balance number. Okay. Each asset they don't have a independent identity in this system. So you can pass them around. You can pass them between layer 1 and layer 2. It's not you can, but you will see extra complexity when you want to do exchanges between layers. That's why the layer 2 solutions today is facing problems on Ethereum, because in Ethereum network, the layer 1 is modeled on the layer 1 is using a account model, which is focused on people, focused on who, not assets. But if you think about Bitcoin, in Bitcoin ledger, it has a asset-focused state model, which is UTXO model. So in our opinion, we need these two requirements for a suitable layer 1 for layer 2. But Bitcoin fits the second requirement, Ethereum fits the first requirement, and none of them fits both of them. Right? So what should we do? That's why we have cell model in Nervos. And what does cell model mean? Cell model is based on UTXO and made a very small generalization on UTXO, which is we turn amount into capacity and data. Amount is an integer. It's just a number. But if we want to create a smart contract system based on UTXO model, we need to generalize amount into arbitrary data. This data is just bytes. It's binary data saved in this cell, the smallest state unit in cell system in our layer 1. And capacity means the maximum size of this cell. You can imagine this cell is a piece of memory in your computer. Okay. It's like I can, in C++, I can unlock a memory and release it. Instead, this system is shared by all users of Nervos network. So anyone can request or buy a certain piece of memory in this system and then transfer them to other people. And you can store your data in your memory in Nervos network. So this is the smallest change of UTXO to support smart contract system. And there is a simple constraint, which is the size of the cell must not exceed the capacity records here. So in Nervos network, the capacity you owned is the token you owned. The capacity is the token. It's the native token in Nervos network. It's like you can buy and sell memories in a computer system. Now once we generalized the basic state unit, we can construct a transaction based on cells. It's the same as Bitcoin. We have inputs and outputs in a transaction. And each transaction is basically a state transition. It's like the transaction means I want to invalidate these two old states and replace them with these two new states. It's just state transition in state machine. These two inputs reference to validate states in history transactions. And each state can only be updated once. It's like in Bitcoin, you can only spend UTXO once. So each transaction is just a state transition. And the invariant here is the sum of input capacity must be larger or equal to sum of output capacity. Now we can write contracts, smart contracts in this system. So we can, as you can see in each input, we have each input is consisted of a reference and a proof. The reference to the old state, and the proof is just like the witness data in Bitcoin. It's some data plus some code. Why do we need to have some code? Why do we need to have a code here? It's because right now we only support lock hash. Okay, I'll skip that.
P2SH.
Yeah, it's because right now we only support things like P2SH in Bitcoin. But the concept is the same. So you need to submit some code when you create this transaction, and this code will be executed in this system. How? Okay. So the data you submitted and the two inputs and the two outputs in the previous transaction will be combined as arguments to the code you submitted in the previous transaction. So the code is submitted here. The code is in this inputs proof, and this data, user submitted data, and this two reference cell and this two new cell will be passed as arguments to this piece of code. And the code will be executed in a virtual machine and return yes or no. If it's yes, the transaction is valid. If it's no, it's invalid and will be rejected by the system. Okay. And in CKB VM, we are using RISC-V instructions. So we choose RISC-V instructions because it's open standard and it's designed for hardware. Instruction set designed for hardware makes much more sense for blockchain because it reduces the risk of hard forks. There will be no new instructions added into RISC-V in future. Right? The standard is already fixed, and RISC-V is quite simple. It has the core instruction set has less than 50 instructions compared to EVM's 74. EVM is a very simple VM, but RISC-V is just more simpler than EVM. And it's quite powerful compared because it has the same ability, like basically the same ability as x86 because it has awesome industrial support. We can compile any GCC supported programming language into RISC-V instruction set. So we are using CKB, we are using RISC-V instructions in CKB VM, which means you will be able to write smart contract in any programming language you like. And we just talked about a simple, one kind of contract in CKB, which is one-time contract. Why do I call it one-time contract? It's because the code is used once. It's not. It will not be saved on blockchain. It will not be saved in blockchain's state. It will be used once and being discarded. These two output is what will be left on blockchain state. But sometimes we want to have durable contract. We want those code be left on blockchain state, and so we can reuse them. It's also easy to do in CKB, in Nervos. So you only need the thing you need to do is extract the code you want to reuse and store it in another cell, and reference the code in another cell in your log script. That's simple. Because all those things are just memory, right? Any tricks you can do in computer memory, you can do here. Okay. So why is this important? What we just did is we created a smart contract system based on UTXO model. Right? We start from UTXO, generalize it a little bit, add a simple virtual machine. So the question is, what's the difference from Ethereum? Ethereum is also a smart contract system. The difference is, if you think about it, in transaction, we store states, not events, in transaction. This is also the difference between Bitcoin and Ethereum. What do I mean by this? Every blockchain system is a replicated state machine. Right? It's the basic abstract model of distributed system. In state machine, we have state and events. Right? Each event it is an input to the current state and will make the state change into a new state. So, if every blockchain is a state machine, you also has two ways to model them, right? to model them. Yeah, you can either store events in a transaction or store states in a transaction. So, for example, in what we call event-focused design, which is Ethereum's model, when a user uses his wallet, he triggers some event in this wallet, and his wallet will wrap this event into a transaction and broadcast this transaction. Right? His wallet is actually broadcast an event to the whole network, and the miner node will process this event, do some computation, and generate new state here. New state are generated on miner nodes. Okay. Now compared to Bitcoin or Nervos, it's using what we call state-focused design. A user uses his wallet. User also trigger events in his wallet, but the wallet will process this event and generate the new states. And the wallet will wrap these new states and construct a transaction and broadcast these new states to network. If you compare these two patterns, okay, so Ethereum broadcasts events in this network, but Bitcoin or Nervos broadcasts new state in this network. So this is why Ethereum is a computation system, because Ethereum network is processing those new events, but Bitcoin or Nervos is only a verification system. They verify those generated new states. That's the difference. So why is this important? Because if you separate generation and verification, it's much more flexible to do this generation part, right? Like in Bitcoin, it doesn't matter how you construct the transaction. You can use Python script. You can use the Bitcoin wallet. You can use like Go to write a generation, to implement a generation algorithm, right? In Bitcoin, generation means how to find those inputs and outputs and compose them into a transaction. It doesn't matter how you do that. Bitcoin only cares about that the inputs amount equals to output amount. That's the verification part. Right? So in Nervos, it's the same. Nervos doesn't care how you generate new states. You can use any programming language you like. You can use a centralized service to generate new states or your personal wallet. It doesn't matter. We only care about if the generated new states is valid or not, or invalid. It's a verification system instead of a computation system. Okay. So this separation between generation and verification also leads to separation of layers naturally. Now you have two layers. Layer 1 is verification. Layer 2 is generation. If you think about like Lightning Network or state channel, all the work they are doing is generation of the final state. Right? I don't care about the intermediate states. I only care about the final states. So that's why in layer 2 or in generation layer, you can use like your wallet or centralized service or multi-party channels or blockchains like Plasma. It doesn't matter. There are a lot of benefits you can get from this separation. More benefits, like the whole blockchain system is much more simple because we just remove the whole generation part, and we have a much more simple state model, what we call cell. In cell, it's just plain binary bytes. Unlike in Ethereum, you have a Merkle-Patricia tree in account. It's much more simple, and simplicity leads to security. We want to make layer 1 much more secure, and that's why we need to keep it simple. And all those separations. And one extra benefit is transaction dependency is much more easy to detect in Bitcoin or Nervos than Ethereum, because the new states are expressed explicitly in transaction. So you can check those dependencies between transactions by using like static analysis. If you want to check the dependencies between Ethereum transactions, you can't do that because there's only events in Ethereum transaction, and you have no idea which part of the state will be accessed or updated by the events. You cannot know the transaction dependency before you really process those transactions. So this is the basis. This is the base of like sharding or parallel processing. Right? Only if I know the dependencies between transactions, I can process them in parallel. You don't need extra state synchronization protocol because the new state is already included in transactions. In Ethereum, you need extra state synchronization protocol. like what Parity did, which has a lot of problems I won't talk about here. Okay. So recap. We want to build a layered network, and we found there are several requirements for this network. So we come up with cell model and to make assets to be the first class citizen in this network. And from cell model we get a state focused design, which leads to separation of generation and verification, which leads back to layered network naturally. Okay. This one. That's the basic idea of what of Nervos network, and we have done a lot of research and engineering. We have much more to do in future. So in Nervos, the layer 1 is using POW consensus. We want to explore how much more potential POW we can exploit. Like, what's the performance limit of a POW? Right? The Bitcoin POW or Ethereum POW can only reach 10 transactions per second. Can we reach 100 or 1,000 with POW? I don't know. This is what Ren is working on, and yeah, we're just doing research here. And light client, we want to make our layer 1 light client friendly, which means we need some kind of proof mechanism that light client can use, so they can know that the data I get is correct, is the genuine longest chain. Cryptographic proof for state verification. Because right now we have no general solution for state verification. We need to write down all those the invariants, the things we want to keep unchanged manually to verify those states. I wonder if we can find a general method to do this automatically, so we can verify all kinds of state transaction, all kinds of state transition automatically. I'm not sure. It seems quite hard. Economics, we have economists helping us to define the economic model of the whole network. And there are also a lot of work to do on layer 2. Like, we need to define the interactive protocol between layer 1 and layer 2. And we also need to define the interoperate protocol between those layer 2 networks. Like, if I have 2 plasma chains, how can I exchange information or assets between these 2 plasma chains without the intervention of layer 1? And I believe there are more layer 2 schemes we will find in future. I'm not sure what they look like, but I believe their existence. That's all. Thank you. Do you have any questions? Please.
Could you please go back to the slide versus state versus event slide?
Okay. This one?
Right, yeah. So in Bitcoin you said the generation also happens, is also the state focused design?
Yeah, Bitcoin is state focused.
Right, but I thought the generation of the new block also happens in the mining node. Or does it not?
Right. So the generation of new block, okay. So state focused design basically means what you broadcast on network.
Okay.
The generation of new block is kind of verification. Because if you think the transactions being included in that new block, the transaction is constructed by users. So the miners, they have no rights to determine the new states. Right? They have no rights to determine how those new outputs look like. It's determined by user here. Miner only verify them and pack them together and brought
The miner can censor transactions.
Yes.
Which is to some degree influencing the contents of the block.
Yes. Maybe Ren can answer that question. So that depends on if you think POW is censorship resistant. If you think it, I'm not sure.
We can add punishment to miners who censor transactions. So in Nervos, each transaction has two phases, a proposal phase and a commitment phase. So if a transaction is valid and proposed for a long time and it's not valid, you can be sure that the miner is deliberately censoring the transaction. As we have cryptographic proof for that, we can forfeit the deposit of the miners. That's just a rough idea, but I'm working on it.
So you said that the lock script itself is not put on the blockchain, but then how do I verify independently that everything's correct?
Okay, I mean here, right?
Yeah.
Yeah. It's like you can, if you compare to Bitcoin, this whole part is like signature in Bitcoin.
Yeah, but in Bitcoin it is included in the signature.
Yeah, right. The signature is included in the blockchain history. It's not in what I call blockchain state. The blockchain state is the whole UTXO set, the current state of the system. So if you include a transaction into blockchain, it will be always there. But the signature or this part will not be in the state. I'm not sure.
But then how would I verify that it's correct? Right? Because in the signature, I need to take the hash of the script and then compare it with whatever the hash was. Right?
Yeah. So yeah, the hash of the code will be in the blockchain state. It's here. The lock is actually lock hash. The lock hash is stored in cell in blockchain state. So when I submit a transaction and want to update this cell, you need to submit the corresponding script whose hash equals to this hash. So it's only this hash is in blockchain state, and you submit the code when you want to update it, and the code will be used and executed only once.
Yeah, that's fine when I want to update it, but when I just want to verify it independently, then I would have to remember all these log scripts, right? To see if they were the correct.
You want to verify what?
The whole state from the beginning, let's say.
Yes.
As an independent third party.
Yes. If you want to start from, like, sync from Genesis block, you will walk through all those histories. Then, in such a scenario, you will see this history log script. But what I mean by one time is you cannot invoke this piece of code in future transactions because it's in history, it's in transaction, not in state. It's like you can only spend UTXO in the current UTXO set, right? You cannot spend transaction output from a not exactly. It's like you cannot reference any data from a signature, from the script PubSig in Bitcoin. So if you think about Compare it to this one. If we extract the code out from the log script and put them in a separate cell, you can reference those code. This data segment here actually stores a piece of code. You can reference the code stored in some cell in your log script. This code is stored in what we call blockchain state because it's in a cell. It can be referenced, but if it's in it's here, it cannot be referenced by other codes.
So as I see it, in Bitcoin, the public nodes have actually two functions. One is remember the entire history. The other is to verify whether some new transactions are valid. To serve only the second purpose, namely to verify whether new transactions are valid, you don't need to remember the entire history.
True. I agree fully with this. Right? So for the verification part,
right. You only need to remember the UTXO set. So I think in Nervos they are proposing that this new public nodes, they don't need to remember the entire history. They only need to verify the new transactions. To serve that purpose, you don't need to remember all the script that has already been fed. You only need to remember the hash of the script that hasn't been fed.
True, but then the difference with Bitcoin is in Bitcoin I can see all the log scripts that were used to come to that point.
Right. There will be a special kind of public nodes that will remember the entire history. But not every public node needs to do that.
Yeah, you can also see those one-time contract in Nervos, but only if the node keeps all the transaction history. I can prune the history and keep only the current state. Okay, any more questions?
So can you clarify how you solve scalability? What kind of scalability you're aiming for?
Okay, by scalability I mean, so the throughput of the system can be scaled to like 1 million transactions per second to support all the activities we need in crypto economy. So how do we reach that kind of throughput is by using layered structure. In layer 1, we don't need that high throughput. Layer 1 only needs like 1,000 transactions per second. And we do all the ordinary business on layer 2, like payments between Ren and me. Those intermediate transactions will be moved from layer 1 to layer 2. That's why the whole network is scaled, because there will be many layer 2 networks. Like there will be channel between Ren and me. There will be channel between me and Frank. The layer 2 there will be multiple layer 2 networks to support for those transactions. And when will there be any interaction between layer 1 and layer 2? In perfect scenario, in ideal scenario, only when there's something bad happen on layer 2 and the user in layer 2 is arguing with the operator or another user in layer 2, they will submit challenge from layer 2 to layer 1. By challenge, I mean some data with proof, and they will use cryptographic proof to argue with each other, who is right, who is wrong, and the system needs to judge those proofs and punish users accordingly. reward and punish user accordingly. In such a way, we can scale the whole network because we move all the ordinary transactions, daily transactions in layer 2. And layer 1 doesn't need to care about them.
So how many layer 2 networks will a user be involved with? Is this hundreds, and how will you manage this as a user?
How many layer 2 networks?
Will I be involved with as a user? Is for every merchant I deal with, or every interaction I have my own?
I think there will be a lot of different networks. There might be a network between only 2 people or 3 people. There also will be a sub-network, like 1,000 people using this sub-network. And there will be like 1 million such layer 2 networks scattered around the globe. Like some of them are channels, some of them are sub-networks. It's like the internet. We have interconnected internet, but we have many local networks. All those local networks will be layer 2. Feel like layer 2 network.
So is there going to be one client that interacts with all layer 2s?
One client interacts with all layer 2s.
So which, I mean, do I have to use a new program for every layer 2?
I see. Yeah, I hope so. Which means we need to have some kind of standards here. Yeah. Now there are so many layer 2 solutions are in competing with each other. We have not seen such a standard yet, but I believe there will be some standard in the future.
Yeah, what if someone creates an inefficient layer 2 network that's constantly using layer 1? So is there a way of stopping people doing that?
It's hard to do so because every transaction happen on layer 1 will cost you some money, basically. So you need to pay transaction fee. If you constantly interact with layer 1, it should be quite expensive to do so. Okay, thank you guys.